In this lesson, we will go over more transformations of functions and relations, taking a look at one of the more complicated ones for grade 11 here, transformations of semicircles. I already mentioned in a previous lesson how certain equations can make a transformation scenario kind of look more complicated than it actually is, and this is one of those examples. This is the equation of a semicircle that has had some transformations applied to it. And just to show you what the what the parent function would look like for this particular graph, it would look like this. And in this case, our radius is in the same position as the 49 here. So really the equation should look like this, where the radius squared is 49. So if you're comparing the parent function here to the transformation equation here, the first thing I want you to notice is that the 49 is actually not one of the transformations. If you remember what the transformation general equation looks like, a times f of k x minus c plus d, and our function here is the semicircle equation. The 49 is not one of those letters. It's not A, it's not K, it's not C, it's not D. It's part of the original function's equation, and that will throw some people off. This happens in other scenarios as well that we'll see later on, specifically the exponential graph, but this is the first time I think that this happens in the parent functions that we've already seen. So that 49 is telling you what the radius of the circle is to start. It is not part of the transformations. So it is your job to recognize that, knowing what the parent function equation looks like. Once you've done that, then you can start to see what are the other transformations that are going on. And hopefully you can now see that the A is the -2. The K value is actually the 3 here. The C is the -1, and there is no plus D in this case. The plus D would be 0. Okay, so that's something that you just need to realize, is really knowing what your parent functions look like in equation form, as well as the table of values and the graphs, to be able to tell what are the transformations that are happening, and are there any numbers in the equation that are part of the original function and not actually a transformation. So I'm not going to go over the transformation of the table of values for this one. Maybe just discuss the fact that the A being a -2 here would stretch the semicircle vertically and also flip it upside down, so a vertical reflection. The 3 here would be a horizontal compression. It looks like a multiplication by 3, but it's actually going to divide all the x values by 3. The C value here is a +1 translation horizontally, so it's going to be moving the semicircle to the right by 1, and again, there is no vertical translation specifically. Moving on to something different here. In a previous lesson, I had mentioned that sometimes a vertical stretch and a horizontal compression can basically do the same kind of thing to a graph, make the graph look exactly the same after one or the other. And same thing for a vertical compression to a horizontal stretch. Those things can somewhat look the same as well. And just to prove that to you with equations, I have a couple of examples here. So I have f of x is equal to 8x to the power of 3, g of x is equal to 2x to the power of 3. So we know that our parent function for a cubic looks something like this. 8x to the power of 3 would be a vertical stretch, so it would make the graph much narrower by stretching it vertically, whereas the horizontal compression here would squish the graph in this way. But could that not mean that the original parent function would therefore end up on the same graph as the vertical stretch? And the answer is yes, because if we actually take the time to expand this 2x to the 3, which means 2x times 2x times 2x. In other words, the outer power is going to affect the inner powers of 1 next to the 2 and the x here, and give us 2 times 2 times 2, which is 8x to the 3. Well, that is the exact same equation as this one here. So it is possible that a vertical stretch can give you the exact same output as a horizontal compression for the same graph because of that. Here's another example with a different function. We've got 4 root x compared to 16x all rooted. And when you have a situation like this one, you can actually consider it as 2 separate roots. The root of 16 is plus or minus 4, but we're going to leave it to just positive 4 here. And that would actually give you the exact same graph as this one. So where the first graph here is a vertical stretch by a factor of 4, over here we have a horizontal compression by a factor of 16, so 1/16 of all your x's, but that would actually end up giving the exact same graph. So your original square root graph looks like this. A vertical stretch by a factor of 4 would make it look like this, but a horizontal compression by a factor of 1/16 would also give you the exact same graph. So because of the way the equations are for certain functions, this is a possibility. And what that means is, when you're asked to go from a graph to an equation, it is sometimes possible to just use a vertical stretch instead of a horizontal compression, unless it's clear that it's both, and especially if they're both different. But sometimes you can get away with just using one instead of the other. And vertical stretches and compressions are a lot easier to work with than horizontal ones. Which leads me into the next part of the lesson here. What if you're asked to go from the graph to an equation instead of the equation to the graph, which is what we've mainly been doing up to this point? I figured I'd write down the strategies first, but these strategies may not make sense until you actually see them applied to an example. So I'll just leave this up here and read through it, but as soon as I get to the examples, we might come back to this slide and just talk about how these strategies make sense. So the first thing you'd want to do by looking at a graph is determine which parent function actually matches the graph the best. And please be careful, parabolas can look like demi-circles, so those two can be somewhat similar sometimes. So you definitely want to be careful about that. But most of the other functions we've seen are relatively different. Since stretches and compressions don't affect the origin point, if you know where the new origin point is, so if you have a graph, and most graphs do cross through 0, 0, at least the ones that we've seen, except for maybe the demi-circle, that point is really nice to be able to tell if the graph has slid left or right or up or down, because once again, multiplying 0 by a number or dividing 0 by a number will not change the answer. So if you can find where the parent function's origin point has moved to, you will know the horizontal and vertical translation, which are your C and D values. The last one's a little bit hard to explain. Again, it'll make more sense when you see the graph, but because we know the original tables of values for the parent functions, from the origin point to the next point in the table of values, we'll usually have a specific distance horizontally and vertically. So if you can find where that point has moved on the transformed graph, and figure out how far horizontally it is and vertically it is, that is usually going to represent the stretching and compressing value of those 2 points. So again, that'll make a little bit more sense when we look at an example, but that is going to be the way that we're going to figure out our A and K values. So let's go see how we can apply these strategies to an actual situation. So here's an example of a graph. I'm hoping that looking at this graph, you will recognize it as one of our parent functions. The parent function would be f of x is equal to x cubed. So cubic graphs usually look like this. And we can figure out what the table of values should be by just remembering to sub them into the original equation here. So negative 2 to the power of 3 would be negative 8, and then negative 1, 0, 1, and 8. So those are our regular points. So let's go through the strategies for our graphing. So I'm going to go back to the screen here. We've just determined which parent function matches the graph the best. So next we're going to look at our horizontal and vertical translations. Can you see on this graph where the new origin point is? So the original origin point is at 0, 0, as you can see in the parent table of values. Where did that move to? Well, I'm hoping you can tell that it moved to here. And that is at a coordinate of negative 1 and 3. Well, that is going to tell us what our C and D values are in our equation. So if we think of what our equation is going to look like, I'm going to call it g of x as the transformed equation. We don't know our A yet. We do know that we're going to have a cubic graph. And we also know that inside of here, we're going to have our C value, and over here, we're going to have our D value. So our C value should be plus 1 because the graph has moved, the origin point moved from 0, 0 to negative 1. And it should also be a plus 3 for our D value because the whole graph has moved up. So we don't know our K yet, if there is one. Sometimes the K is going to be a 1, but in this case it won't. And we don't know our A value. So that's what we need to figure out next. Now, I did choose an example that has both an A and a K value because I want to discuss how we would do that. Here's the way that I usually proceed. So the next step in our strategies is the change in distance between the origin and the next point. So that's what we want to look at, okay? So what is the change in distance between the origin and the next point supposed to be? Well, the x values are supposed to move over by a positive 1, and then the y values are supposed to go up by a positive 1 as well. Well, let's look at what happens in the graph over here. If I move over from my origin point by a distance of 1, now a horizontal distance of 1 is this full distance here. If I move that full distance there, I don't even see the graph. So because this is the only thing I have to work with, I'm assuming that that is not what is happening here. I'm not moving over by 1 and going up by 1. In fact, I'm moving to the left to go to my next point. Either the whole graph has flipped upside down or it has reflected horizontally, okay? It's supposed to go over to this way and up, and it clearly goes downwards. So that's another way of thinking of it. What I like to do is find a clean point that is going to help guide me towards what is happening with this graph. And I can either go right or left to do this, but you can see that there's a clean point here or here, okay? So how far over did I move, left or right, to get to that point? Well, again, I'm supposed to move over a full 1, but I didn't move over a full 1. What fraction of 1 did I move over? Can you see that it is 1/4? So this distance right here is 1/4 of a full 1. That is kind of guiding me towards the fact that my k value is based on the number 1/4. Now, we know that it's always a 1 over k relationship with what is in the bracket here. So if I put 1/4 in k, I'm actually going to end up with a 4. Now, you can think of it this way. It looks like I'm dividing my x distance by 4. That means I'm going to put a multiplication by 4 inside my bracket. Now, that clean point is how far up from my origin. Well, it's supposed to only be 1 up, but it looks like it's actually 2 up. And that is kind of hinting towards the fact that I'm getting a stretch of 2. So I'm going to put a 2 in the position of my a value because I am stretching by a factor of 2 to get up to that point, which is the only clean point I can see, and then I am moving 1/4 to the left or right. Now, we also have to take into consideration that moving this way, where I'm supposed to be moving upwards, I'm moving downwards, and the reverse is true too. If I move left, I'm supposed to be moving downwards and I'm moving upwards. So this whole graph has been flipped upside down or has a horizontal reflection. So I have a choice here. I can either put the negative sign here, or I can put the negative sign here. Since it doesn't make a difference, I'm actually going to choose to put it out in front because I feel like that's the best position for the negative sign. And it wouldn't actually make a difference because if I did put it next to the 4 here, I could bring it out of the bracket because cubing a negative number still gives a negative number, and it would join the -2 anyway. So it doesn't really matter where we put the negative sign. And if we look below, I actually did copy and paste the equation that I had used to generate this graph from Desmos, and as you can see, it is the exact same equation. So going back to that last bullet point here of using the origin in the next point in the table, I'm hoping that that's a little bit clearer. You're basically trying to look at how did it change the origin point here to the next point, goes up by 1 and over by 1. Well, that's not happening in the graph, so how do we use that information to be able to figure out what the horizontal compressions and stretches might be and what are the vertical stretches and compressions? This is a skill that takes some practice, and I cannot show you every possible scenario that you're going to encounter. Let's look at one more example here, just to show you that you can have various different scenarios. So here is the graph that I'm giving you. I am expecting you to be able to recognize this graph as a square root function. You are supposed to know what the square root function's original table of values looks like. So 0, 1, 4, 9 are the x values we usually use. 0, 1, 2, and 3 would be the square roots of those, which give us our y values. And clearly this graph is not following that pattern. The regular square root graph looks like this. This graph is not doing that. So how do we go about figuring out what the actual transformations are? Well, once again, start with the origin point of the graph, which is supposed to be here. Where has it moved to? It has moved to here. That is going to give us our C value of 4, so it is a horizontal translation. This time there is no vertical. It stayed on the x-axis, so it did not move up or down. So I do know my C value is 4. So I can actually start writing the equation already. I'll just use spaces to represent what I don't know. So we've got our a value, which we don't know yet, and then we'd have our square root function. Inside our square root function, we have potentially a k, and then we'd have x minus 4. So plugging in the c gives us that. And then we'd have a plus 0 at the end here, which we don't have to write because there is no up and down transformation. Now, clearly this graph is not oriented in the right direction. Normally, as I had posted before, the graph would look like that. So it definitely looks like it's been flipped. Now, which way has it been flipped? Well, if it was a vertical reflection, the graph would probably be down here. Because that's not the case, it definitely looks like there's a horizontal reflection to have made it flip in direction this way. So that's going to mean a negative sign for the horizontal transformation, and we usually just write a -1 to show that for our k value, so it's a reflection. Now, that might be something that we're going to need to change in a minute, depending on whether or not there's been a horizontal stretch or compression. But let's take a look at the next step in our suggested method of doing this. What is the normal distance between the origin point and the next point? Well, we usually go over by 1 and up by 1. Well, I know that this is horizontally reflected, so it's not going to be going to the right by 1. But if I go left by 1, how high up do I go, and do I end up at a clean point? And the answer is yes. I do end up at a clean point going over by 1. So that is a hint that there is no horizontal stretch or compression, because going over by 1 from the original origin point's new transformed point and then going up to the graph brings me to a clean point. So in this case, we're going to then conclude that there's only a vertical stretch or compression potentially. Now, I'm supposed to go up by 1, but I went up by 3, and that is telling me that this should be a vertical stretch by a factor of 3. And that's basically the procedure to follow to find your equations. Now, you're going to see here that the equation that I had on Desmos is a little bit different. This is how I had typed it into Desmos. I just wanted to discuss the fact that I ended up with the factored version of the equation here. But you may see that equation as the non-factored version, and that would just be by multiplying the -1 into the bracket here. So you'd have -x, -1 times x, and then -1 times -4, which would give you +4, and then we have the exact same answer. The only way to master this is to practice it. So you can expect that a teacher would probably give you a worksheet on this. I will give my students a worksheet on this. And you just need to work your way through trying to figure out, okay, well, I think the hardest part is the third step of the suggested strategies here. But once you start to see, okay, what is my original origin point, and what's the next point in the table supposed to be? Well, where did I actually move to get to the next point? Try to pick a clean point that you can use to figure that out, and usually you'll be able to figure out what your A and K values are by doing that. We'll end the lesson there. See you soon, folks.